So today's lecture is going to be talking about complexity. So we've talked about this before. Sequential search is where you have a target value in a list of values, and the way that you go about searching it is starting at the beginning and moving down to the end. So if you look in this example, you'll see that there's an array from 0 to 16, and each index is associated with a value, and that the values are in ascending order, meaning going from lowest to highest. So one way you can search is saying, let's say for example I wanted to find the value 42, and you don't know in the list where 42 is. You want to find out what index it's at. So one way you could do is you could start at the beginning, and you just go to the next and the next and the next until you hit it. And if you hit a number greater than 42 without hitting 42, then you know that it's not in the list. So in this example, you'd start out at index 0, and again, because it's an array, you just know the starting point. You can reach any index in the array, but you have to start at the beginning. And so what it does is, this is off a little bit, but the idea is that it went all the way up to 42. And so what this is saying mathematically is that on average, you'd expect that if there's n elements in the list, meaning like, let's say n is 100, on average you'd expect it to be your search to be n divided by 2. So if you had 100 elements, you'd expect on average that your average search would be, you'd hit about 50 values till you find it. And the reason is that sometimes they'd be above the 50th element, sometimes they'd be below, but on average you'd run about having to go to the middle list before you hit the number you're looking for. Binary search is another technique that we've kind of briefly mentioned, and it's pretty slick. Again, you have to have an ordered list. It doesn't do you any good if it's not ordered. And that's true with the sequential search too. If it's not ordered, you'd have to go through the whole list to find out if it's in there or not. But since it's ordered, you can use some different types of algorithms to try to find it sooner. And so in this one, if you're looking at 42, what the idea is that you divide the list in half each time. And so here you'd have a minimum, a min, and a max. And what you do is you go to the midpoint, because you know the length of the array. So you say, let me start in the middle of the array and see what that value is. So in this case it's 30, and you know that 42 is greater than 30. So what you do is then just look between, and again these are off a little bit, but the idea is that you look between your previous search point and your maximum, you divide it in half. And so in this case, let's say that the half point actually was 68. Well, you know that 42 is less than 68, so then you'd also do this again. And again, for some reason these are off, but the idea is each time you're dealing with a smaller half of the list, because you know that you had already looked at the middle, so you don't need to look lower than that. And you know that the midpoint of the highest one was where you, or the minimum of the highest one was the previous one where you had to go to. So each time you just basically divide it in half and divide it in half till you get ranged in on the value that you want. And so what that's saying is, in this case, it took only 3 comparisons to get to that. So that's a lot faster than with the other list where you had to go through more than 3 to find it. And that's what we like in computer science, when we can do things more efficiently and faster by being smarter about how we set things up. So how much better is binary search than sequential search? Well, so this is one of the things that's key with computer science, is being able to quantify how we measure efficiency. And it can be relative to different things. It can be computing speed, it can be how much memory is used. Those are kind of the common ones, but there's other metrics also possible. Most commonly is referred to when you're working at runtime. And so there's kind of a formal way that's done to quantify runtime efficiency. And so some of these basic assumptions that you use when you're calculating out runtime efficiency is you assume that any single Java statement takes the same amount of time to run. This isn't true in reality, but it's a good approximation and it's useful. So with what this is it's not exact, but it gives you levels of magnitude, and that's what you actually care about. Because you want to know, okay, does this take me, can I run this, in one time, two times, 1,000 times, 10,000 times? Once you get the difference between 2 and 10,000 times, then that's a decent difference. But the difference between 2 and 4 really isn't. So what that means is that it's not precise, but it's a good approximation. So the method's runtime is measured by the total number of statements inside the method body. And so we'll see an example of this in a second. And so if there's a loop that repeats n times, it's n times the number of statements in the body. And again, we'll see an example of this in a second. So here's one example. It's showing that these first three statements, each one, let's say it takes time 1 to run, so that's 3. We next have this statement that's n, so we don't know exactly how big n is, but we do know that it's a variable that we can use, and we know that there's one statement in there. So that one is just, that statement can get run up to n times. This one, there's 3 statements in that similar type of body, so that one can get run up 3 times n. There's 3 statements. Each one could be executed n times. So what you do is you take this and you add them all up, and here you see that this is 4n plus 3. So this is kind of like a math formula to approximate how much code, the code execution. So we'll look at another example now to kind of give you a little bit of a contrast there. So that's 4n plus 3. The second one shows you that there's a loop up front, but it's a nested loop. And so in this case it's n squared, because that one statement could be run n times n times, or n squared. So this is showing you that this statement executes a lot more than the other one, which was just one for loop. Now if we look at this one, it's just the 4 statements, and it's one for loop. So those 4 statements will only be executed up to n times. And so how this would get added together is you'd have n squared plus 4n. So this is expressing mathematically kind of the runtime associated with it. And so this is where we get into ways of talking about that. And so when you're talking about an algorithm, you're really interested in kind of like a good approximation, not an exact number. So this is saying here, look, you got this algorithm that runs 0.4n cubed plus 25n squared plus 8n plus 17. Well, so anytime when you're looking at this, what you kind of do is you assume that, or look at it as n gets extremely large. And so if you're familiar with kind of taking numbers to limits, whatever's biggest will dominate the rest of the formula. So in this case, constants are ignored because they really have minimal impact compared to n. And the other thing is that it's really the highest order term within a statement that'll dominate it. So in this formula here, even though this is kind of like a more precise way of stating the approximation, this n cubed is still the big guy that dominates everything. So rather than saying, if somebody was to ask us, what's for your algorithm, what's the big O notation, that's the term that's used for it. And it's just, from computer science, the term that it says, it'd say it's n cubed, because everything else kind of gets ignored, and just this n cubed factor is what's focused on. So this here shows O(n) cubed. That's, rather than, you would never see anyone express the algorithm growth rate as this, you'd see it like big O(n) cubed. And so this is showing you how the typical kind of big O notation measures. This one is like the ideal. It's constant, and it's big O(1). And that means that no matter what size n you have, it always takes the same amount of time to execute. And so this is, in computer science, this is like the best as far as for efficiency and speed. Logarithmic is log base 2n. This is, like, for example, what binary search is. This is also really good. Even though as n gets bigger, it increases slightly. And so we'll look at a graph to kind of see this. So this is a class of logarithmic ones. Linear is ON, and this moves as your data gets bigger, so does your runtime. And so this means, they move together. This still isn't horrible, but it's not as good as, constant or logarithmic. Log linear is n times log n. So this is slightly bigger than linear, but still pretty good. So these are the kind of classes, in reality, with computer science, most algorithms that are considered fast would be at this point. Here you get into quadratic, cubic. These are also called polynomial. These aren't end of the world, but things get slower pretty quick when they're this big. And the one that you really want to try to find an algorithm that doesn't operate at is what's called exponential. And that's when the n is actually the exponent. And this gets big really fast. So it's showing you kind of to give you an idea of, maybe an O1 operates in 10 milliseconds. This one, 5 to the 10 to the 61 years. The problem with exponential algorithms is you can get so big that you never even be able to compute them. Like, we think that computers are really fast and can do a lot of stuff. In reality, there's plenty of algorithms that there's no way that we ever have enough time, even with all the computer power, to calculate. And so as you move on your coursework, you'll start to learn what some of those algorithms are. But this is just showing the different, how they kind of graph out as n, which is this bottom element, gets bigger. And so O1 doesn't even show up. It's this, basically flat line. This is like the best. Showing you that O log n really isn't that much different. So again, this is great. ON, it does increase linearly, but it's not, it's still not expanding rapidly as the amount of data or the amount of statements you're working on gets bigger. And then this shows as you get n log n squared, exponential, and factorial is one of the biggest. I mean, basically with a factorial type algorithm, once you get past a few elements, it gets huge really fast. So these types of algorithms are really hard to compute. And so as a computer scientist, you try to avoid algorithms like that. And if you have an algorithm like this that's in place, and you can figure out an algorithm that does the same thing that's in here, you get your name in kind of computer science history. Because there are some outstanding ones that are in this area that everybody's always trying to find something that, rather than being here, could even be here or here. And there's plenty of ones that haven't, where nobody's come up with a better way to do something. So with the sequential search, talking about the kind of trying to put this in big O notation. So we said that on average, n divided by 2 elements are visited. Well, again, we said that constants are ignored, so this would be this would be a big O n. So it increases linearly. As your data gets bigger, so does your search time in a linear fashion. So if this doubled, on average, it would take twice as long you'd have to do twice as many operations to find your number. And it shows you that it's n. Binary search, on the other hand, because it eliminates half each time, this is what we're talking about, where this is an example of a logarithmic algorithm. And so it can find elements really fast. So this is a type of search that we like. And so, for example, in class we're talking about binary search trees. That would have a log n, big O log n complexity. And that's it.